Good afternoon. My name is Eyal, and I will start with a situation that you may have had coming here in the morning or coming to San Francisco. You need to pack. You have a bag. Capacity is limited on the bag, and more realistically, maybe this is what you need to pack, what you want to pack. It does not all fit in the bag. And you need to decide what to take and what not to take. And this is called the knapsack 0-1 problem. You have a list of items. Each item can either go in or not. And each item has a value to you, but it also has a weight or volume or something that there is a limit on. So let's say the bag is limited to a certain weight, and you cannot fit everything in there. So you try to maximize, you want to maximize the value that goes in the bag without reaching the weight limit. So you need to figure out what is the best combination of things that you pack in the bag. So it just happens that I have a Python program here that will solve the problem. Of course, you can go over all the combinations, do an exhaustive search, and find the best solution. But usually, if you have enough items, it's not going to be practical. So here is a program that makes it somewhat practical. It has a list of items, not exactly those items, but they're limited to 400 pounds. So here it found a combination that gives you 396 pounds, and that's the value, that's the best value it could find. And let's move to another problem. Here you see cities on a map. I think it's in Germany. And you just have cities that you know the locations. You can tell the distances between the cities. And you want to find a route that goes through all the cities and back to the first city and do it with the minimum distance. And this is a well-known problem called the traveling salesman problem from the days that those salesmen had to basically go to all these towns and visit every place, and maybe did it with a horse and carriage. And here's another program that will solve that, or at least try to. And it takes a few seconds, and that's the solution that is found. It is usually in these problems, visually you can pretty much tell if it's the best solution or not. When it's not, it's sort of obvious. So I need to just make this go away. What else? One more problem. This is just a function that we want to optimize. We want to find the minima of, or the minimum, but in this case, that function has actually 4 equally low minima. There are 4 of them that you can see in the middle of those blue places. And we just want to just optimize it and over this range. You see the range is between -5 and 5 and -5 and 5, x and y, and we want to find at least one of these. So here's a program that will do that. It will just run, and you see it found a collection of points, but some of them are exactly on target, on one of them. Now we can run again and maybe find one of the other ones. But instead, we can actually modify this program a little bit and see if we can find all four of them at the same time. So it runs a little slower, but it pretty much did that. It found actually a bunch of scattered solutions, but the best of them are exactly, or pretty much, on target. And if we go back to the presentation, so we saw 3 seemingly different problems. The interesting thing is that the programs that we saw were very similar. The solution for all these problems was pretty much the same, even though we changed the problem. The part that really changed between the 3 kinds of problems that we saw was the problem. The solution was about the same, with some tweaks and modifications. So this is a very powerful proposition here. We have something that solves all kinds of problems without changing much the basic underlying algorithm. So what is this? And how can we apply it to machine learning? These are the 2 questions I'm going to try to address in this presentation today. So one thing these problems do have in common is that they are optimization problems of sorts. Here we try to optimize, get the best value we can into this bag. Here we try to to minimize the distance. Here we try to minimize the function. It's just that the problem domains were very different. The conditions that we were doing it were different. But the idea of solving them is the same, and it comes from, it's implemented with genetic algorithms. So genetic algorithms are a way to solve a plethora of problems of this sort. And a lot of problems that we encounter in engineering, in science, and in everyday life are optimization problems. We want to get the best solution. Machine learning actually is an optimization problem as well, and actually several aspects of machine learning are optimization problems, and we will hopefully see it later. And genetic algorithm is a good way, in many cases, to deal with these problems and produce high-quality solutions in a reasonable amount of time. But let's see how they work. So genetic algorithms are based on the Darwinian evolution principles, and this is not the right one. Okay, sorry. That was supposed to be the laser pointer, but I'll give up on the laser pointer, I guess. So the main thing about the Darwinian evolution is that the idea is that solutions, or we are sort of solutions to the problems that the environment presents to us. We, or whoever is dealing with evolution, the subject of the evolution, and the ones who deal best with the problems have a better chance to survive, and they have the best chance to have offspring, and they transfer those traits that made them better into their offspring. So over time, those traits get more accentuated in the population. The population evolves towards better and better ways of dealing with the environment, which for us, it's meaning better solutions. So our problem is sort of an environment. We create a population of solutions for it. Those solutions over time get better and better because we make sure that the better ones of them survive and basically give those features that they have, those building blocks that they have into their offspring. And this is how it's done. It's really very simple. You start with some random population. Well, it's not completely random, but it's random within the problem. So for example, if we go back to, going the wrong direction. If you're going back here, there will be random numbers in that range between, it will be x and y between -5 and 5. There will be a bunch of random like that. And if it was this problem, it would be random order of the cities, etc. So we start with random solutions, and then we do this magic. We do evolution on these solutions, and at the end of the process, we decide to stop at some point, and we say, okay, let's stop here. And now the solutions that we have evolved and hopefully are good enough, and we can use them. And this is what's inside that main loop that we call evolution. What you do is also relatively simple. You have a generation of solutions. You want to make a better generation out of that. So you evaluate your population. Each individual in the population gets a score according to how well it solved the problem. And then we apply some kind of selection to select who will be the parents of the next generation. And we try to do it in a way so the better individual will have better chances to be parents. And then we actually do that crossover mating. We take them and we create offspring from them. And then we can also do here and there, we can put some mutation into the game. So the offspring can, here and there, can change a little bit. So they won't be exactly just what their parents used to be or what we had before. It could be something completely new. So how is it implemented? So the idea is pretty simple, and it makes sense. Let's see how it's implemented. To implement it, the first thing we need to do is to represent every solution in a way that we can deal with it with genetic operations. So every solution that we consider here gets a representation. And the easiest representation, and the most common in many cases, is the binary string or binary list. So for example, that would have worked well for our backpack or knapsack problem. Each item, let's say the first item was your keyboard, the second item was your other keyboard, and then your backlit keyboard. And the 0, 1 will just say, do we pack it or do we not pack it? So this is how we would represent a certain, if you had 9 items, that would be a representation of any solution for the packing. It will say which one you packed and which one you didn't. And the interesting thing is that the genetic algorithm itself doesn't really care what it represents, as long as we have a way to evaluate it. And there are all kinds of other representations for other common issues or problems. So the problem with the traveling salesman person, where we had a list of cities and we needed to find out the order, you can have a chromosome like the ordered list. I just was too lazy to draw it nicely, so I just wrote it down there. So you will have indices arranged in some order. And then for the third problem that we saw, you can just take floating point numbers. In our case, it was just X and Y, so you would just have two items in there. And now once we decided how to represent the solution, and by the way, it doesn't have to be that. It can be anything you can imagine and you can work with. Tree is another way to represent maybe somewhat more complicated problems or solutions, or a combination of all these can also be. You could combine them into an integer with a float and whatever else makes up your solution. The main work of understanding, or the only place that you really have to understand what this solution represents is whether you go to evaluate it. There is something called the fitness function, and it calculates it needs to calculate how good this solution is. So in the case of the backpack problem, it will add up all the values of the items that have a 1 there, representing them. It will also look at the weight, and if the weight is too large, if it's invalid, then it can just decide that it's 0 or put some penalty into it. In the case of the cities, the fitness function will say, okay, we have city number 2, city number 3, let's measure the distance between them, then city number 5, let's measure the distance. It will sum up the distances, and you will come up with the distance that we want to minimize. That would be our fitness, the actual distance. So other than that, the genetic algorithm, and usually the way I see it at least, the fitness function is part of the problem, not part of the solution. It's encapsulated in the problem description. How do you take that string and you apply it to the problem and you calculate what the value is? So after evaluation comes the selection. So here we basically try to give advantage to the ones that have the better, that evaluated better than others, and have them become parents of the next generation. So we actually select them randomly, but we want the better ones to get a better chance. The ones who are not so good still have a chance because they may have something in them that will eventually prove useful. Originally, the way that it was done or thought of was called a bias roulette or just roulette wheel. And basically, let me try again for the laser. Is this the laser? Okay, I can't do that. So the idea is that if here we only have 6 for the demonstration purposes. If we have 6 individuals and this is the fitness and we want at the maximum, then obviously E is the best, D is the worst, and we can translate it to percentages, make this pie chart. So you see here, E has the 40% chances, and D has like 3% or something like that. That's a shame. So let me try this again. But last time it turned the whole thing off. No, that is not working for me. Where was I? Okay. I will either stand down there or I will just try to be more descriptive. So the 40%, the bigger pie slice, what?
Active presentation mode and use your mouse.
Okay, we'll do that. You can see the mouse. Oh, great. So here we see this is the E. It has the best selection, it has like 40% chance. This little sliver is D. And then somebody say, you know, that pie chart looks just like a roulette. So let's put this stopping point here, and we just roll the roulette, and if we keep doing that, then it will stop. And we take the place that it stops, and we will choose that. So it will give the chances of the selection to be pretty much that. Practically, there are a lot of issues with that. So we don't normally use that, or we use it in all kinds of ways that are corrected or adjusted. The most useful one seems to be what we call tournament selection. Tournament selection is very simple. It's also very simple to implement. Tournament usually is either size 2 or 3. You see here size 3. So a size 3 means that randomly we select 3 individuals, and then we take the best of them. So here F was the best of the 3. So we did the F, then we keep doing it and keep doing it until we have enough, basically the same amount that we started with. If we have 20 in the population or 6 here, you will end with another 6 that are going to be the parents. Tournament selection actually is very interesting, not just simple, but interesting because when we do tournament selection, we don't actually have to know exactly what they evaluated to. We just have to know which one is better. It's enough to if we can compare them to each other. So imagine that we are trying to solve a problem where it doesn't quantify with an equation. Or let's say that for example, we're asking people for their opinion. Let's say that we're looking for a combination of colors that just look good. So we ask the person, do you like this better, or do you like which one looks more like what you're looking for? And they can say, okay, I like this better. They don't have to actually calculate anything. Or let's say that we are evaluating some algorithm that plays a game, and then let them play against each other if you don't have a better way to evaluate it. The tournament becomes a real tournament. So that makes it sort of useful. So now that we selected, we kept doing the selection until we have enough, basically the same size of population we have enough parents. Some of them will be selected more than once. Now we take them and we try to create offspring from them. So this is the best way to describe it with binary strings. That's called a single point crossover. You can also do 2-point crossover. And the idea is you take some genetic material from one parent, some genetic material from another parent, exchange them. Now you had 2 parents, now you have 2 offspring. Obviously, it's more complicated when you deal with an ordered list or with floating point number, but the ideas are the same. We create valid offspring that have some of the material of each parent. And the idea is that you have building blocks. This genetic material contains building blocks, and the better individuals have better building blocks. We're trying to collect them together. This is what the evolution does. It brings all these building blocks together that solve the problem the best, and eventually we get very good solutions. Now, mutation is another thing that helps us. Sometimes we just need to explore some areas that we didn't, and we don't just want to rely on what we started with. So mutation in the binary case is very simple, like this. You can do other things. You can decide to reverse the order. You can take this half and all kinds of things that you feel like doing. Can be creative. Genetic algorithms let you be very creative, actually. So differences from traditional algorithms are sort of obvious. We have a population rather than one solution that we modify. That is usually the case. We look at the representation, and the behavior is somewhat random, driven, but with probability. We give better probabilities to the ones that are better. And also, the mutation is based on probability, and there are probabilities for certain things to happen. The advantages of those algorithms is, first, there's something called global optimization. I'm just showing this picture quickly. A lot of algorithms are based on gradient descent, and they can get stuck in a place that looks like a minimum, but it's not the best. It's suboptimal. It's a local minimum, while the real minimum is somewhere else. Genetic algorithm is a lot more resilient to that because it searches different areas and it jumps around, and it doesn't get stuck just because that area looks better. And like we saw before, it can handle all kinds of representation. It can handle things that don't even have a representation. We doesn't need to have derivatives of the functions that it deals with, unlike some other algorithms. And another thing is it lends itself very well to concurrency because most of the operations that we saw are sort of embarrassingly parallel. The selection, the evaluation, all of them, we can just do it separately and concurrently. Resilience to noise is just because you keep doing similar things over and over with different combinations. So noise is when you try the same thing twice and you don't get exactly the same result. For example, when you ask a person what their opinion was, or you ask a lot of people, or when you read measurements from something that there is some noise that goes in. Because the genetic algorithms keeps doing different combinations, it sort of filters the noise out. The last thing is sort of interesting, ongoing learning. We have situations that we want to keep learning. We didn't really solve the problem completely. Let's say that we are trying to see, for example, what people's opinions are, and we try to build a website that people will like. And we end up changing it until we think we found the best combination, maybe of colors and fonts and whatever. But slowly, maybe a month later or 2 months later, people will start liking things a little bit differently. Your environment changes. So you think you solved the problem, but the problem may have changed over time. Not the problems that we saw today, but there are cases where the problem that you're solving is an ongoing problem that keeps changing. As long as it changes slowly enough, you can just keep running your evolution. And when changes are introduced, your evolution will follow. And your solutions now that were the best may not be the best anymore, and they will be replaced with others. So it lets us do that continuously. Of course, they have disadvantages too. So the first thing is that you do need to define the genetic representation of the solutions and the operations that you do on that. In many cases, it's been done already, and it fits within things that exist, and you can just copy that. In other cases, you can be somewhat creative and maybe combine things, or maybe come up with new things, but you do need to do that. It could be computationally intensive because you have a population. You keep evaluating a whole population, not just one. And concurrency here can help. Caching can help too, because you find yourself in many cases evaluating something that maybe you evaluated before. And then the risk of premature convergence means that sometimes, this is a little bit like the local minimum issues that we saw. Sometimes you will come to a point where the whole population looks the same. You had like one very good solution or two that took over. Because they were so good, they basically took over the population. And once the whole population looks the same, you're stuck. You can't really go anywhere other than maybe a mutation that somehow will save the day. Most mutations don't. Most mutations will give you bad solutions. But you're basically now stuck, and therefore a key element of genetic algorithms is to maintain diversity of the population. If you don't maintain diversity, and there are ways to do that, if you get the population to be too similar, then you might get stuck. And it's okay when it happens towards the end, perhaps, because then you found already maybe the best solutions. But if it happens early in the game, then you're done, and you have to be careful not to have that happen. And also, there is no guaranteed best solution. For example, if you did an exhaustive search, it might have taken you forever, but you know that at the end you covered you found the best solution. This theoretically you can run forever and maybe never find the best solution. It could happen. Or you don't know, or you ran it for a while and you need to stop at some point, and then you say, okay, is this really the best solution? Sometimes you can tell. It depends on the problem. That the solution is really the best that can be, but sometimes you can't. So with genetic algorithms, the idea is that practically you get good solutions, but it's not guaranteed that you will get the best. Sometimes that's the best you can do pretty much with any other algorithm. There are some algorithms that are guaranteed to find the best solution in infinite amount. In infinite amount. So if you run it forever, you'll find the best. You know that you find the best solution. Here, you're not guaranteed that, but it's not practical anyways to run something infinitely. So it's not really, in my eyes, not such a. Okay, so the programs that I ran, they use the DEEP framework. They're Python programs, and they're written with DEEP. So actually, genetic algorithm is simple enough that you can just write programs directly in Python or any other language. And you can find a lot of examples on the web of people who did that, and they just wrote their own. But using a framework always gives you the advantages that they optimize it, they already debugged it, and then they have all the operators already in place. In the case of Deep, it also gives you all kind of other capabilities. It lets you, it has this container that you can define new classes from all classes, and you can define operators from other operators. I don't have time to really go into it, but it makes things very easy to follow. And it has reasonable documentation. I think, in my eyes, one of the issues there is that the documentation was obviously written by developers. So it could have been a little more clear. But then there are also all kind of other Python frameworks, and in any language you will find a framework. So how do we apply this to machine learning? Let's talk about supervised machine learning in particular. Supervised machine learning, basically you try to find a mapping. You have some model in there, which is sort of a black box in many cases. The model tries to map inputs to outputs by tuning all kind of parameters internally. For example, in neural networks, these parameters will be the weights of the nodes in the network. In a decision tree, those parameters will be like where to split, on what feature to split, what input, and how to build a tree. Learning here, the supervised learning, means that we give examples. We tell the model, okay, this is the input, this should be the output. This is the input, this should be the output. The model comes out with its own output and says, okay, there is a difference. Let me tweak my parameters to minimize the difference. I keep doing it, minimizing the difference. So basically, a learning algorithm that comes with the model is really an optimization algorithm. It tries to minimize the error or maximize the accuracy, or maybe there are some other metrics that we can apply, but we always try to either maximize or minimize something. So actually, learning is a kind of optimization, supervised learning at least. Classification, which is one prominent use case, is where we have the inputs are called features, the outputs are sort of labels or categories, and for a certain set of values in the features, we want to say, okay, this is this level or that level, meaning one of the outputs will go high, the rest of them will go low, and we select a category. And let's look at the famous or sort of well-studied data set called the zoo animal data set. And here we have about 110 perhaps different animals. Each animal has certain features. It will tell you, most of them are Boolean. We can see them here. For example, an antelope, if we look at the list of features, it will say something, okay, it has hair, it does not have feathers, it does not have fins, it has a tail, etc. And the folder probably says it has 4 legs. And at the end, the one at the end is the category that antelope falls into, which is a mammal. And the bass will be probably has fins, has scales, etc. Doesn't have legs, and it's a fish. And then you have, go back here, you will have reptiles, birds, etc. So you have seven classes of animals, 7 categories, and 16 features. Let me just, I think I sort of skipped a little bit too fast here, but I said that learning is an optimization process. Let's go back here. Therefore, actually, whenever we have a classifier, we can replace the algorithm that tries to, each classifier comes with its own algorithm, like the tree. Decision tree will have an algorithm that builds the tree. The neural networks will have the back propagation that tries to adjust the weights. What they do is optimize those parameters to give us the best results. And that means that actually we could have replaced those algorithms with a genetic algorithm as well. And a lot of people actually had done it, especially with neural networks. We're not going to look into that because one thing, by now I think most of these models have very specialized algorithms, very well tuned and tried and true, and it's probably not going, it could be interesting basically to try to replace some genetic algorithms. They may find some solutions that are more resilient to suboptimal local minima, but I'm not going to look into that. That's what I was going to say, and so I'm going to look at something a little bit different. Like I said, learning has other aspects that are minimization, not just the learning itself. So when we look at the zoo animal data set, what we see here is that we have 16 features that we can use to decide what kind of animal it is, but do we really need all 16? Maybe we can do, so basically this is the classifier here. It has those features, hair, feathers, etc., and it has 7 classes. Feature selection says that maybe we don't need all those features. Maybe we want to select a subset of those features. Why would we do that? Why not use all the information we have? It sounds like the more information, the better. Practically, it's actually the opposite. More information can introduce noise, can confuse the model, the learning. Basically, there could be redundant features, irrelevant features, and if we just basically take only a subset of features, we can actually come up with a better model. And you know that with Occam's razor, the simpler the model, the better it will generalize. So if we can do the same work with less features, it will work better. So we're going to try to do that. So how can we do? So this is an optimization problem of another sort. We want to find the best features, the best set of features that will give us, in this case, let's say the best accuracy of the model. So we actually wrap, it's called a wrapper type of feature selection. We take the classifier and we wrap it with this algorithm that tries different combination of features, and every time we go through the learning and we want to see when we are going to do it better. So again, we could do an exhaustive search, try all the combinations of the features, but we want to do it more efficiently and try to do it, for example, with a genetic algorithm. So because we have 16 features, we can use, and we just want to know if the feature is included or not, we can use a binary just like the same as the knapsack algorithm. I can use pretty much the same solution that I used for that knapsack. So I can use that. I can use the tournament selection, 2-point crossover. These are just things that are very standard with binary chromosome, pretty much what we saw in the examples. And just like it worked for the knapsack problem, it should hopefully work for this problem. So one thing that we need to take care of is how to convert that into a fitness value, right? The fitness function needs to take that binary string and tell us how well the classifier did when we only selected those features that have a 1 on them. So how do we do that? We can just remove, we have a data frame with all those, we have the data set of the animals. We remove those columns from it that represent those features that we're not going to use. And then we can do, we can measure the accuracy of the learning algorithm, either by taking a training set. For example, one thing that people do is take 80%, for example, to train the algorithm, the model, and then the other 20% to test it and take the accuracy from that. Or even better, we can do something like a K-fold. Let's say that we divide it to 5. We divide the 100 and some examples that we have to 5 equal groups. And each time we use 4 of them to train the algorithm or the model, and we use the 5th one to test it. And then we run that 5 times, and we calculate the mean. So if we do that, then I can show you, first, let me show you that this is the, I run decision tree classifier on the problem with all the features selected. Do you see? Oh, you don't see. I'm sorry. I need to do that. Okay, sorry. So when I ran it, I ran here just one run where I put all the features being selected. All of them are 1, and I asked the fitness function to tell me what the accuracy was. So the fitness function took all the features, took just the original set, and ran a decision tree classifier, and used the K-fold cross-validation of 5, and the accuracy is about 91%. And now let me run a genetic algorithm that tries, which is, like I said, exactly like the knapsack problem. It tries to find the best combination. What you see here is the generations progress. This is the generation on the left. The left column is the generation. the max will show us the best of the generation, and the average will show us the average accuracy of the generation. You can see that even in the very first generation that was random, we just chose random column to remove. Even then, we were already better than the 91%. And this is a graph that shows you the best is the red and the average is the green. So as generations went by, we were able to improve the accuracy a little bit more and a little bit more. And then where we stopped, this is what we get. Let's go back. Maybe I need to kill that. Just close that so the program will end. What we see here is that these are the best 5 that we found. I did another trick here, and I put a small penalty on the number of features that were used. So even though all these 5 solutions have accuracy of 97%, the best of them is the one that has the least features, which is 6, because I penalize it a little bit less. The other ones were penalized. So you see that the fitness is a little bit better on this because I only penalize it by 6 of 1,000. That was more done as a tiebreaker. So if you have two, to make sure that if you have 2 classifiers that give you the same result, one of them uses less features, we will give it the advantage. So what we see here actually, if I go back here, is that with all 16 features, without doing the feature selection, we had 91% accuracy. When we used only 6 out of the 16, which if we chose them wisely, we went up to 97%. And these happen to be those 6. So it's enough to know these things about an animal in this data set to know what it is. So this was one use case that we can apply genetic algorithms to supervised learning. Another thing that we can do has to do with hyperparameters. So hyperparameter is sort of a headache, usually, I think. Yeah?
Sorry, in the previous case, were you training a neural network with those parameters that it selected every single time?
Yes, but it wasn't a neural network, it was a decision tree.
Oh.
A neural network would take longer. So, yeah. But yes, like I said, it's a wrapper. So every time that you present it with a possible combination, you go and train it. And if I was expecting sort of that somebody might ask me if I heard about principal component analysis or anything like this. Actually, not the same thing. You can use them both. You can use PCA to reduce, if you have a lot of features, to reduce them because it makes sort of fake features. And then you can take those and still select because the PCA does not really care about, it does not really look at the actual model. It does not care about what results you get out of the model. It just says, okay, these features have more information than those. But I'm willing to talk more about it after the session if anybody's interested. The hyperparameters, which is a completely different subject, is where every model usually has some other parameters that are not changing during the learning, that we set them before the learning and they are kept that way. And they usually have default values. So if you look at this classifier, and sklearn is the Python machine learning, a very nice library, very useful library. And you can see, for example, that this algorithm has all kind of parameters that you can set when you create the classifier. That's before you ran the learning process. When you create the classifier, you call the constructor. So, for example, the number of estimator, the learning rate, and the type of algorithm that we use. And that's sort of an interesting example because the number of estimator is integer, the learning rate is a float, and the algorithm is sort of categorical. We have one of 2 choices here. And pretty much every classifier will have all kind of parameters like that. One thing that data scientists do, a very common thing to do, is to run a grid search. And then in grid search, you sort of create a grid. You said, okay, the number of estimators, let's run these values. Let's check all these 10 values. For the learning rate, we will also check 10 values, but we define them as a logarithmic. So it will be the -2 means 0.01. The 0 means actually 1. And we have 10 values for the learning rate. And then algorithm, you only have these 2 values because these are the only 2 that are acceptable here. And now we just run grid. So what does the grid search do? It takes these parameters here, where it says param grid down there. We tell it what we want to score on, and then we tell it how the scoring is done. So it could be like the cross-validation, K-fold cross-validation. And when we run that, what is it going to do? An exhaustive search, right? It's going to, in this case, there are only 200 combinations. There is 10 for the first one, 10 for the second one, 2 for the last one. So it's going to run through all the 200 combinations, and eventually at the end, it will tell you which was the best. So that again is a problem that we can solve with genetic algorithms, because we have all these combinations. We want to find the best combination. We don't want to do an exhaustive search because it can take a long time. And here, by the way, again, it's like your question before. Every time you try those parameters, you have to go through the learning, and you have to see what the result is, and then you know what is the best result. So the genetic algorithm, hopefully, if you use that, you will just try less times, and you won't have to do the exhaustive search. Even though this was only 200 combinations to begin with, what happens is that the people who made the deep library, they actually made a special package called sklearndeep, where you can use something very similar to the grid search, but it's called evolutionary algorithm search. It has the same parameters, but at the end, you give it some parameters that go into a genetic algorithm that is built in, and it will actually run a genetic search. So hopefully, it will not need to run through all the combinations, and it will find a solution faster. They actually have an example online where they show a huge difference in one case that they tested, that was a lot faster than going through all the combinations. But some of it is sometimes a matter of luck, but it is definitely something to consider. But still, we are limited to the combinations that we decided in the grid, right? We are limited to 10, 20, 30. What if the best solution is actually 22 and some other combination that is not one of those that we covered with the grid? So we can do the grid very, very, very dense. Or we can try to do something else. Why don't we run a genetic algorithm that just searches everything and finds the best solution? That might be a better way to go about it. So, but it's an interesting situation, because we have integers, we have float number, and then you have something that is like a choice of several values. So if we wanted to create a genetic algorithm, we would have to maybe work a little harder and define some representation that takes into account that you have an integer, a float, and something else, and define how we do the crossover, etc. I did something a lot more lazy than that, and I said, let's just presume they're all floats. So I define them like that. Basically, I said they're all floats. We'll just say what is the boundaries of the floats. Like in the function that we had between -5 and 5 on the x, -5 and 5 on the y. So now I'm running the same thing, but I tell it there are 3 variables. One of them is between 1 and 100, and that's the number of estimators. One of them is between 0, 0, 1, and 1, which is the learning rate. And the other one is between 0 and 1. And I run it just like that with floating point. And whenever I go to evaluate the function, then I translate and transform them back to what they are. So the n estimators, because it is an integer, I just round the number. I could have done maybe floor or something better, but I would round the number, and it will turn into an integer. Learning rate, I don't have to do anything because it's a float already. And the algorithm, I basically use that parameters that between 0 and 1. I round it, and I use it as an index to choose between the two algorithms. So basically, I took those float numbers, converted them back to those parameters, and I run this. And that, by the way, relates also to something that happens in nature. Sometimes the genes are not exactly what you see. When you translate the genes into an actual being, some of the things will change along the way. This is called genotype to phenotype mapping, but it's not that important here. I think it just was an easier way to do things. So I won't be able to run it. It's a little bit longer, but I was able to get better results here in the examples I was trying. So this is pretty much what I wanted to talk about. If you want to learn more about me, I suggest you come tomorrow to, there is, where is it? I don't see it here. Here it is. Tomorrow there is a panel session. I will participate there, and we will get more personal, I think, there. And then it will also be a discussion that you can participate. But I also wanted to tell you that I've been working on a genetic algorithms book, and hopefully it will come out at the end of the year. And if you scan that, you will join a list where I will let you know when the book comes out, and I'm going to have 1 or 2 at least live discussions about genetic algorithms, and we can go a little bit more into detail, some things that we covered. So this is what I had to say, and I hope that was useful. If you have any questions, we can try to answer. Thank you very much.